Welcome to The Explainer. Today we're jumping right into projectile motion. It's the physics that describes everything from a thrown baseball to a satellite orbiting the planet. We're going to uncover these surprisingly simple rules that are hiding behind these really complex-looking paths.
So, let's start with a puzzle. How can something be moving at a steady speed and speeding up at the exact same time? It sounds like a total paradox, right? But this is the central mystery of projectile motion, and by the end of this, you'll see exactly how it works.
Okay, so what is projectile motion, officially? It's the two-dimensional path an object takes when you throw it into the air. We call the object itself the projectile, and we call its curved path the trajectory. And the key here, for our ideal model, is that the only force we're going to worry about is the constant downward pull of gravity.
Now, to make our lives easier and to actually solve these problems, physicists make a few key assumptions. First, we're going to pretend air resistance doesn't exist. We also neglect the effect of the Earth spinning, and finally, we assume that the force of gravity is constant, always pulling straight down with an acceleration we call g. These assumptions create the ideal model that lets us see the physics clearly.
All right, get ready, because this next idea is the absolute key to unlocking everything about projectile motion. The secret is to stop looking at it as one complicated, curving path. Instead, you have to see it for what it really is. Two much simpler motions happening completely separately at the exact same time.
Let's break that down. Think about it in two directions. Horizontally, along the x-axis, there are no forces acting on our projectile, right? So its horizontal speed never, ever changes. It's constant. But vertically, along the y-axis, gravity is always pulling it down. This gives it a constant downward acceleration, which we call negative g.
And this right here is the main takeaway. The horizontal and vertical motions are completely independent. They literally don't care about each other. How fast the object is moving forward has zero impact on how fast it's falling. And how fast it's falling has zero impact on its forward speed. They're like two separate stories being told by the same object at the same time.
So now that we have that core principle locked in, let's see it in action in the most common scenario, when you launch something at an angle to the ground. When you launch something at an angle, that initial velocity has both an upward part and a forward part. To analyze it using our new principle of independence, we have to mathematically split that single launch velocity into its horizontal and its vertical components. And we do this using some basic trigonometry. Just picture that initial velocity as the long side, the hypotenuse of a right-angled triangle. The cosine of the launch angle gives us the piece of that velocity that's pointed horizontally, our VIX, and the sine of the angle gives us the piece that's pointed vertically, our VIY. These two values are our starting points.
Okay, here's where the magic happens. Now that we've split the motion into two simple, independent parts, we can use our standard equations of motion, what physicists call the kinematic equations, to predict everything about its flight, how high it's going to go, how long it'll be in the air, and just how far it'll travel.
So, first up, how high is this thing going to go? What's the maximum height it's going to reach in its trajectory?
The logic here is really important, so let's walk through it. First, the concept. Think about the very, very peak of that arc. The object is still moving forward, sure, but for one single instant, it stops moving up before it starts to fall. That means its vertical velocity is zero at that one point. Once we know that, we can grab an equation of motion, set that final vertical velocity to zero, and solve for the vertical distance. And boom, that gives us this final formula for the maximum height, h.
All right, next big question. How long is the projectile going to stay in the air? This is its total time of flight.
Let's start with the concept again. If we assume our projectile lands at the same height it was launched from, then its total vertical journey is zero, right? It ended up right back where it started, vertically speaking. So we can take another one of our kinematic equations, set the vertical displacement y to zero, and just solve for time. This gives us the formula for the total time of flight, t.
And finally, for the big one, how far did it actually travel horizontally? This is the projectile's range.
And this calculation is just beautifully simple. Because of our core principle, the horizontal motion is just constant velocity, so distance equals speed times time. We just take that constant horizontal speed multiplied by the total time it was in the air, which we just found, and when we substitute everything in, it simplifies down to this really elegant formula for the range, r.
So we've got the theory, we've got the formulas, now let's talk about how to use this stuff, and also we need to acknowledge the limitations of our perfect little physics model.
If you want to launch something as far as humanly possible, what's the magic angle? Well, in this perfect world without any air resistance, it's exactly 45 degrees. That angle gives you the perfect balance between upward motion to keep it in the air and forward motion to send it down range.
Now why 45 degrees? Well, if you remember that range formula, it has a sine of 2 theta term in it. And from math class, you'll know the sine function hits its maximum value when its input is 90 degrees. So for the longest range, 2 theta has to equal 90, which means the launch angle, theta, must be 45 degrees. And here's another cool trick of the math. Complementary angles, ones that add up to 90, like 30 and 60 degrees, will give you the exact same range. Crazy, right? One will be a high looping arc, the other a low, fast one, but they'll land in the same spot.
Of course, in the real world, we have air resistance. So how does that change things? Well, our ideal trajectory is a perfect, beautiful, symmetrical parabola. But air resistance acts like a drag force, a constant brake, slowing the projectile down. This means the actual trajectory is shorter and tends to be a bit steeper on the way down. Both the maximal height and the range are going to be reduced compared to our ideal calculations.
Let's end with a little brain teaser. Picture a plane flying perfectly level. It drops a package the exact moment it's directly above a target on the ground. But the package always lands far ahead of the target. It overshoots it. Based on that principle of independence of motion we talked about, why does that happen? Think about the horizontal velocity that package has the very instant it's released. Thanks for watching.